Okay, next up we have Dale Kocevski talking to us about the insights into early supermassive black hole growth from the CEERS survey. So, yeah, please take it away.
All right, thank you. All right, thank you, everyone. It's great to be back in Santa Cruz after several years away. And in fact, I'm going to talk about some work we've been doing with the CEERS survey looking into the growth of early black holes out to the epoch of reionization. So this is all work done in collaboration with Guillermo Barro, Steve Finkelstein. I'll talk a little bit about a high redshift source that Rebecca Larson has detected, and a large cast of characters from the CEERS collaboration. So one of the key unanswered questions or open questions in AGN science is the nature of the original black hole seed population. There have been a variety of formation mechanisms proposed that predict a range of initial seed masses. This includes the collapse of a POP3 star that produces a light seed, with typical masses on the order of 100 solar masses, to the direct collapse scenario that leads to heavy seeds that directly form into, have masses on the order of 10 to the 4, 10 to the 5 solar masses. The direct collapse scenario is predicted to occur before a galaxy forms a substantial fraction of its stars. And so one of the predictions of this second scenario is that galaxies may start with an overmassive black hole to begin with. And so one of the ways in which we can constrain these scenarios is to look at the black hole galaxy scaling relationships at early times to see whether these early galaxies actually have a host overmassive black holes, whether these galaxies sit above the local relationship. And so this is one of the motivations to look for high redshift quasars and actually try to constrain their host masses as well as their black hole masses. But one of the things that we've seen from simulations is that not all quasars are well suited for this task. If you go into simulations where we have a variety of predictions as to whether early galaxies will have an overmassive or undermassive black hole, so that's what's shown here. This is a deviation from the local relationship, black hole mass versus a galaxy mass as a function of redshift. There's a variety of different simulations here, a variety of different predictions as to whether things will be undermassive or overmassive. And the thing I'm trying to convey here is that if you go and just sample bright quasars, let's say you could actually detect the mass of the host of those bright quasars. If you could do that really well, those bright quasars don't actually trace out to predictions from the larger black hole population in these simulations. So bright quasars are rare enough that they basically don't actually bear out the prediction that these simulations produce. But if we go to faint quasars, here I'm talking about bright quasars, I'm talking about things with volumetric luminosities greater than about 10 to the 46 ergs per second. If we go to faint quasars, about 2 to 3 decs fainter, here we actually start seeing those predictions traced out. And so this just tells us that bright quasars are relatively rare. They're not good. They're not representative of the normal black hole population. And so this motivates the search for these faint quasars at higher redshifts. Now, all the data that I'll be using for this talk comes from the CEERS survey. Raj mentioned CEERS briefly earlier. CEERS is the Cosmic Evolution Early Release Science Survey. All of the CEERS data, as I'm sure most of you guys are aware, is public. We have a GitHub website where you can basically grab all of our public releases. CEERS is basically a early release science program. We've imaged and again spectroscopy of about 100 square arc minutes of the EGS field. So here's our layout. The gray area here is the previous generation WIFC3 imaging from candles, and then we've got our 3 instruments, NIRCam, MIRI, and NIRSpec there. The NIRCam imaging goes from 1 micron to about 4 microns. Our MIRI imaging covers about from 560 to about 25 microns, and then we have our NIRSpec observations. The reason why we chose EGS for the CEERS survey is that one of the roll angles in which EGS is visible allows us to basically just walk up the WIFC3 mosaic and ensure that we basically get overlapping parallel observations. And so our strategy here was to simply start with our NIRCam observations. In fact, NIRSpec is in prime and NIRCam in parallel, but in the way that I'm showing this, basically we just argue that we're moving around this way. And so we've basically just tiled these such that we end up getting overlapping. This is slowing overlapping parallel observations, and then we actually come backwards and take our MIRI observations and can come back down. And then we've, just for good measure, we've added GRISM observations, slitless GRISM observations with NIRCam there. So the key point here is that at the end of the day, we've got several pointings where we get overlapping observations of all three observing modes. We've got basically the MIRI observations here. We've got near-spec observations, NIRCam imaging, and then we get near-spec, NIRCam slitless spectroscopy as well. And so that was really the key point that we were trying to accomplish with CEERS, is essentially overlapping observations so we could test multiple observing modes on the same galaxy. Now, we've heard about the NIRCam observations and their power to pick up high redshift galaxies a lot already today. One of the things I was initially interested in with our NIRCam observations was simply looking at the rest frame optical morphologies of galaxies at intermediate redshifts, so redshifts 3 to 5 or so. And so this is just an example of an X-ray detected AGN as seen in the CANDLE survey. This is a source at redshift 3.53. It was an X-ray detected source. We knew it was there. You really can't make out its morphology in the WFC3 imaging. And then, of course, it pops out really nicely in our NIRCam observations, where we can see the disk and a nice bulge component at the center there. And so one of the first papers that we put out with CEERS was simply looking at the morphologies of X-ray detected AGN in this data set. So here are 5 X-ray luminous AGN at redshifts greater than 3. This was the first 5 X-ray sources detected in the first round of our CANDLES observations. The contours here are the X-ray contours, and then in the background there we've just got the NIRCam imaging. One of the nice things that we found out was that there were several sources that are basically misidentified. The hosts of the X-ray sources are misidentified. In this case, this source here, this is the X-ray centroid. This was previously identified, matched to that large spiral at redshift 2 in the foreground. In fact, the host is this little small compact source at redshift 4.1 that's much better aligned with the X-ray centroid than the disk galaxy. But that source is basically invisible at WFC3 at 1.6 microns. And so one of the things we did, in addition to looking at their morphologies, was just look at the rest frame optical colors, or UVJ colors. And what we found was that all but one source essentially sits in the quiescent region of the UVJ diagram. The only source that doesn't sit in the UVJ in the quiescent region is the singular quasar in the source, the one broadline point-like source sitting down here. So this is somewhat surprising. We heard earlier today that some of these really massive galaxies early on, quiescent galaxies early on, need a fast mechanism to shut down their star formation. And what we're finding is the most massive galaxies at redshifts 3 to 4 that we're seeing in CEERS that are X-ray detected are in fact also quiescent. So remember, there's not a lot of, you don't have a lot of time to quench these systems at redshift 4. And so we're looking at these things that are basically in a post-starburst phase, and we're actually seeing that they're X-ray bright. However, if we want to get back to figuring out the initial seed population, the black hole seed population, we need to turn to our spectroscopy. And this is where our near-spec MSA observations come in. When we started designing our near-spec observations this past fall, one of the things we did was try to take care to select interesting objects from the literature. These are 2 examples of such sources. CEERS 2782 was a candidate faint quasar identified by Masafusa Inoue. This is basically a source that has what looks like a power law SED, consistent with a type 1 QSO, with some strong emission lines bumping up some of the filters there, some of the magnitudes. And then a second source was CEERS 746. This is a source that Ivo Lebet detected. It was thought to be at redshift 8.13. This is one of these universe-breaking massive galaxies at redshift 8. And that's the SED of that source. The source is shown here. And so we made sure to put both of these sources on an MSA slit. And we basically observed them with the G140, G235, and G395 medium band filters. And so these guys got spectra with a resolution of about an R of 1,000 for both of these. And so what we ended up finding, the folks at Space Telescope put up made us this nice graphic for both of these sources. And essentially what we found is that both sources showed a broad component to their H-alpha emission. That's this little magenta line here. So here's the actual real data. Here's 2782. We see very strong, narrow O3 lines, an H beta line there, and here's H alpha, and you can squint, you can maybe see that H alpha is a little bit wider than our O3 line, and so here's our best fit to this thing. And so there is a broad component here that has a full width half maximum of about 2,000 kilometers per second. We fold in the luminosity of the source. That gives us a black hole mass of about 10 to the 7 solar masses. This maybe is not too surprising because recall 2782 was selected to be a candidate faint quasar based on its STD. But what was more surprising is that this massive galaxy at redshift 8 that Eva Lebet detected was in fact at redshift 5.6, and this source also has a broad component to its H alpha line. And so there is that broad component sitting there. The full width half max of that component was about 1,800 kilometers per second, again returning a mass, a black hole mass of about 10 to the 7 solar masses. Both of these, I will point out that both of these sources, in this source in particular, O3 is detected with higher signal noise than H alpha, and yet we detect no broad component in that oxygen 3. This is one of the reasons why we ultimately decided that the broadline emission was coming from an AGN as opposed to an outflow. We would expect to see that outflow signature in our forbidden lines as well, but we don't. We actually only see it in H alpha. H beta is detected lower signal noise. We can't detect that broadline component in the H beta as well, but it's not present in O3. So when we look at the volumetric luminosity of these sources as a function of their black hole mass, what we find is that these sources sit about 2 to 3 decks fainter or below the volumetric luminosity of the pre-JWC sample of bright quasars at redshift 4 to 7. And so essentially, these are the pre-JWC quasars up here. Local AGN essentially sit down here. These two sources are actually closer to local AGN than they are these distant quasars that we previously knew about, both in terms of their black hole mass and their volumetric luminosity, just kind of highlighting the power of JWC to detect these faint, low mass AGN at redshifts 5 and 6. As we've already heard before, these high redshift AGN don't actually stand out in terms of their emission line properties. And so if we look at the BBT diagram here on the left or the ONO diagram on the right, both of these sources lie in the region of these diagrams where you might expect to find regular star-forming galaxies. Now, that's not to say, as Lisa already pointed out, this is not to say that this contradicts the broadline detection. This is where you expect to find low luminosity AGN, or excuse me, low metallicity AGN. And so it's just telling us that we can no longer use these traditional tracks to pick out sources. And in fact, this tells us that, pick out these AGN, and it tells us that these broadline detections may actually be one of the few ways we could actually pick up these distant AGN. Now, the thing that I find the most surprising about all of both of these sources is that they're not unique. They're not that rare either. When we start looking through our spectroscopy, we find lots of examples of other sources that also have this relatively strong broad component superimposed onto a relatively narrow H-alpha emission line. So these are 6 examples. We've now seen lots of other examples of faint broadline AGN detected in both with GRISM spectroscopy as well as near-spec observations. But it does look like there's a large sample, large population of these sources. And so we could actually measure the black hole mass for all of these. If we put them up on our scaling relationship, one of the things that I've done for the purposes of this plot is simply assume that all the light that we see from the galaxies, from these quasars, is coming from their host galaxy. We know that's not the case because in some of these sources, their SEDs look like a power law. It looks like all the light is coming from the quasar. But if we just assume that all the light is coming from a galaxy, this places an upper limit on the amount of mass that the host can have. And so here we basically just put upper limits on all of these sources. And what we find is that all of these sources are scattering above the local black hole galaxy mass relationship. Now, we've known for a while that quasars, bright quasars, scatter above the local relationship, and this has often been thought to be the result of a selection bias, that these things are basically, we're only picking up the brightest things, and so we're scattering above that local relationship. And what we're finding now is that even as we probe to fainter volumetric luminosities, lower black hole masses, we're still scattering above that local relationship. Now, on the surface, this appears to favor the overmassive black hole scenario, that basically galaxies in early times have overmassive black holes at their center. But I say that with a huge caveat that we haven't yet modeled our incompleteness. We don't know whether what we can't detect below the relationship. And so this is something for future work to basically figure out whether we can actually detect things sitting below that local relationship. And it could very well be that this is consistent with that local relationship. But on the surface, we are still scattering above that local relationship. Now, if this hints that the overmassive black hole scenario is maybe more likely, one of the strongest constraints we have on these two scenarios comes from a broadline AGN that we've detected at redshift 8.67. This is a source that Rebecca Larson presented in her 2023 paper from earlier this year. And this source is, you can see a whole range of lines here. If we can zoom in on H beta in this case, we see that, again, we get a broad component with a full width half max of about 1,500 kilometers per second, gives a black hole mass of about 10 to the 7 solar masses. This source is detected early enough that it alone places some interesting constraints on how it must have formed. And so we're detecting this thing back when the universe is just under 600 million years old, and it is much, it's basically, if this is our bright quasars in the pre-JWST era, this thing sits down here. Here's the other two previous sources that I talked about. CEERS 1019 can either have been formed back, let's say, at a redshift of 15. If we put it, so here is redshift versus black hole mass. Quasar is a bright quasar sample. Here's where a CEERS 1019 falls. And if this thing formed at a redshift of 15, you could have basically a direct collapse scenario where we have a relatively massive black hole that then just grows via Eddington accretion, and that would basically explain the black hole mass that you detect at close to redshift 9. The only way this could possibly be formed via a light seed is that if you had a stellar remnant that formed at much earlier time, so closer to redshift 20, and then it would have to have grown via super Eddington accretion. So essentially, this step function here is basically episodes, the black hole experiencing episodes of super Eddington accretion that is basically bumping it up. In the last 3 minutes that I have, I just want to mention that one of the two sources that I first mentioned, this source that Eva LeVay detected, has a relatively unique spectral energy distribution where it basically has this, as Caitlin mentioned, what looks like a UV excess superimposed onto a relatively red galaxy. There's two ways that you can explain this SED. One could be that this is basically a dusty galaxy, massive galaxy with a mass of like 10 to the 10.5, with a unobscured AGN emitting some of the light at short wavelengths, or it could be a low mass galaxy with some AGN light at long wavelengths. But if you look at the morphology of this source, it is point-like at all wavelengths. And so these models would predict that the galaxy should be contributing most of the light at long wavelengths or most of the light at short wavelengths. But in fact, it's unresolved at all wavelengths. And so one of the things we proposed in our paper is that what we're seeing here is basically just all QSO light. We're looking at a reddened QSO with a scattered blue component that is contributing, that's producing that UV excess. And so this could be due to patchy obscuration, for example. It could be that our direct line of sight to the central engine is heavily obscured, and that produces the reddened QSO. But then we have a scattered light that is basically leaking out that gives us that blue component. This would only need to be about 1 to 2% of the overall emission from the AGN to explain that UV excess. And so this is a very similar explanation that's been given for heavily obscured dusty galaxies in the past. And as Guillermo will talk about in his talk, you can actually pick out galaxies like this using a simple color plot, and it looks like they're ubiquitous. I'll leave this to Guillermo to talk about, but it looks like there are dozens of sources that have this relatively red SED with this UV excess on the blue end. And so it looks like we may actually just be seeing a tip of the iceberg, that there may be a large population of these heavily obscured quasars. I'll just say that if you look at the morphologies of all these sources, they're all point-like. There's basically none of these sources that have this UV excess have extended morphologies, and so it looks like they really are point-like. And Sandra, how am I doing?
You can definitely.
Okay. All right. I'll say really quickly, one of the questions we've been trying to grapple is, do we see any sources like this at lower redshifts? One of the things you could do is simply take your QSO. Here's that QSO spectrum with a heavily obscured source with a flat UV component. Here's our selection bands. This is Guillermo will talk about his selection in a second, but this is basically just using different bands to measure the slope of the SED at various parts of the wavelength, various wavelength ranges. This is at redshift 4.5 to 6, but as you move to lower redshifts, you can basically just shift your band passes to basically measure the same part of the SED and find sources that have this red color plus this UV excess. And so in addition to this, you can simply do a cut on size. So this is half-light radius versus magnitude. And you pick things that look like stars. So here the blue things here are stars. The red, all this stuff are things that have a red spectral slope. And these are the things that might look unresolved. And what you find out is that the redshift distribution of these sources is very different than the redshift distribution of relatively red sources. Our sources with red optical color peak at redshifts 2 to 3. These sources that are both red and point-like essentially start to emerge at redshifts 4 or so. And so it looks like we might be seeing the emergence of these faint, heavily obscured AGN at redshifts greater than 4 that have this red color with this UV excess that might be due to dust scattering. So I'll end it there and throw up my summary slide and take any questions you guys have.
Thank you, Dave. Are there any questions? Yes.
Yeah, thanks for the very nice talk. So I have a question about your black hole mass measurements. So in principle, when you're using the Virier estimate to measure masses, there is a AGN luminosity term in it. So for those faint AGN in those galaxies, how uncertain would you think those AGN luminosity terms are?
Yeah, so that's a great question. So in our paper, we actually do produce two black hole masses. One, assuming that the light is actually, the long wavelength light is from the galaxy and that there's no obscuration in the AGN, and one where the AGN is actually heavily obscured and the luminosity gets bumped up. And so I mentioned that the black hole mass for a heavily obscured one is 10 to the 7. It could be as high as 10 to the 8. So there's a range there based on how much obscuration, how obscured that. So that's absolutely because you need that luminosity component in the black hole mass. That's right.
Any other questions? Sandy?
I'd just like to say that we wrote a paper a while ago, Chen et al., in which we suggested that quasar black hole masses would be related to the quenching black hole masses that galaxies would have as they moved over a putative quenching boundary. And we concluded that that boundary would move with time and be higher back in the past. And this would help to explain the fact that more distant black holes would have a higher 0 point in the black hole galaxy mass relation. So just mentioning that point and encouraging you to think about it in your interpretation.
Thank you.
Just maybe a final question about point sources. Are we sure that they are not brown dwarfs?
I personally have not checked if they're brown dwarfs, but yeah, I know we have folks in CEERS working on brown dwarfs that we could do this, but no, we don't know.
Okay, let's thank Dale again. Thank you.